So hello, everyone. Good morning. Thank you for being here so early. And welcome to this plenary talk this morning. So my name is Gianna Cauzzi, and together with Alexandra Trischler, who's joining us on Zoom, we are the chairs of Symposium 372, the era of multi-messenger solar physics, which concludes today with this plenary session. So I'm sure that you're all familiar with the idea of multi-messenger astrophysics, which has been at the forefront of research in recent years, especially thanks to the spectacular detection of gravitational waves created by distant and massive objects like black holes. However, I want to remember that studying the sun and the heliosphere has been a multi-messenger effort ever since Carrington in 1859, when he happened to see through his telescope in England the photons of the white light emission of a solar flare. And then a day or two later, the world was dazzled by the aurora caused by the energetic particles from that flare that slammed into the Earth's magnetosphere. This effort has continued throughout the decades by combining remote sensing of the electromagnetic radiation with in situ measures of particles and fields as provided by spacecrafts to understand the solar wind and space weather. Or also, as we saw yesterday, using helioseismology and neutrinos to understand the solar interior. This multi-messenger approach to study our star and its immediate environment is now reaching whole new levels, with the recent completion and operation of several flagship facilities, each one with spectacular and unique diagnostic capabilities. This is indeed the topic of our plenary talk today by Dr. Valentin Martinez-Pillet of the US National Solar Observatory. Dr. Martinez-Pillet is a world-renowned expert in solar polarimetry. The presence of magnetic fields within the solar atmosphere imprints subtle and intricate signatures to the light emitted by the atmospheric plasma, in particular to its polarization, as we all know. So within his career, Dr. Martinez-Pillet has pioneered analysis techniques devoted at deciphering such signatures, as well as all-important calibration techniques for both ground and space-based instrumentation to assure that these tiny and rapidly changing polarization signals are properly measured. Such techniques are now the worldwide standard and allow us to reliably obtain insight on the physical properties of the highly structured, rapidly evolving solar atmosphere. Among the many instrumental projects that have benefited from insight, I will highlight that Dr. Martinez-Pillet was the PI of the highly successful Imaging Magnetograph Experiment, or IMAX, that flew on the Sunrise stratospheric balloon in 2009-2013, as well as a co-I of the Polarimetric and Heliospheric Imager, or PHI, for Solar Orbiter, which is currently in orbit and providing fantastic new results, as we will see during this talk. Dr. Martinez-Pillet has devoted many years to service to the community, including as member of the Solar System Working Group of the European Space Agency, or ESA. Of particular relevance to this audience, I will recall that he's been the president of the IAU Commission 12, Solar Radiation Structure, between the 2006 and 2009, and then the president of what was called then Division 2, Sun and Heliosphere, which is now Division E, during the years 2009-2012. Dr. Martinez-Pillet has been the director of the US National Solar Observatory since 2013. And for those of you that are not familiar, the main charge to the National Solar Observatory is that of building and operating state-of-the-art observational facilities for use by both the national and the international community. In late 2021, the NSO completed construction of its new flagship facility, the Daniel K. Inouye Solar Telescope, or DKIST, a 4-meter aperture optical infrared telescope which is devoted to study the detailed workings of the sun and its corona. The commissioning phase has started early this year, and we already saw some fantastic new data during the symposium. In the coming years, the combination of these amazing new observational capabilities with advanced numerical modeling and computational techniques promises many new insights into our nearby star that will undoubtedly serve as a stepping stone for deeper understanding of our universe. Now, it's my great pleasure to welcome our plenary speaker, Dr. Valentin Martinez-Pillet. Please join me. Thank you.
Thank you, Jana. This is the most impressive introduction I have ever had as a speaker. Thank you all for coming this morning to what is the plenary session for IAUS Symposium 372. As the title says, what we've been doing in the symposium is discussing the multi-messenger era that is unfolding for solar and heliospheric physics. The symposium has ended. We have already had the discussions. And I prepared my talk before the symposium, and I was surprised how many of the things that are included in my talk is actually what we've been discussing, and I'm going to be going through my talk and telling you what I learned during the symposium, which was a lot. That means that both Jana and Ali did a great job bringing speakers, and we got an update on this multi-messenger era for solar and heliospheric physics. So multi-messenger, what do we mean solar astronomers by multi-messenger? We're trying to understand how the sun creates and controls the heliosphere. But we're not using gravitational waves. What are our messengers? And there are a number of ways of explaining these messengers, but I think this picture in here really shows beautifully the messengers that we're using for the creation of the heliosphere. Jana was going back to the Carrington event in the 19th century. I think really quantitatively speaking, this multi-messenger era started with the launch of Ulysses in the 1990s. This image in here really shows that understanding how the sun is creating the heliosphere is multi-messenger, and we need to have multi-messenger approaches for understanding how they are all created. For many of you in the audience, you know what this image is. It's very popular within solar and heliospheric physics. But I'm going to unpack the information here for our broader astronomical community. Because it really will tell, okay, these are the messengers that they are using. This is why they are calling multi-messenger this problem of understanding the heliosphere and astrospheres. So the first thing that I want to call your attention is the background image. The background image is a composite of 3 images. There is an image of the solar corona on disk in here. This is taken by the EIT instrument on board the SOHO mission. And then there are 2 additional images that show the off-limb corona. This one in here, the inner corona, is from a telescope on the ground. It's really hard to observe the inner corona from space. So this is from a coronagraph that is operated by the High Altitude Observatory in Mauna Loa. And you do see this inner corona in the annular cycle over here. And then there is the extended corona. The extended corona, again, is coming from the SOHO mission, from the LASCO instrument, another coronagraph. So here you have a picture of how the solar corona is on disk, off-limb. But these are telescopes. We are detecting electromagnetic waves, and this is our first messenger. What are the other messengers? Well, on top of the image, you see this graphic, which was 360 around the sun. And what this graphic tells us, as you can read in here, is the speed of particles. This is the speed of the solar wind. And this is what Ulysses was measuring in situ. After going through Jupiter, Jupiter got Ulysses out of the ecliptic, and it was able to go through the poles at distances of several astronomical units. And Ulysses was measuring the particles. So this is our second messenger, measuring particles and measuring the solar wind and the speed. And you see that here there are some fluctuations. These fluctuations is not noise. This is of solar origin. But it's kind of relatively homogeneous over the north pole of the sun. And the same for the south pole of the sun, relatively homogeneous. But then when you go into the ecliptic and the solar equator, you see a more patchy distribution of velocities. You see something that is changing a lot more, and on average, smaller speeds. So here we have this second messenger, but I hope you can see that the top part has a red color, and the bottom part has a blue color. Red color means magnetic fields going out of the sun, and blue means into the sun. So Ulysses not only was measuring the particles, he was also measuring locally the magnetic fields, the orientation of the magnetic fields. These measurings of magnetic and actually electric fields is our third messenger, and all of them are important. This is why we call it multi-messenger. And why is multi-messenger? Because you probably can see that there is a relation between the image and what Ulysses was measuring. This is an image of the sun, and these measurements by Ulysses were taken sometimes at 5 astronomical units, sometimes at 2 astronomical units. But from seeing how this corona looks like, you can tell, okay, well, when it is kind of this dark type of corona, you get this very fast, very high-speed solar wind. This is what we call the fast solar wind. Same for the South Pole in here. But near the ecliptic, we get this brighter corona. The entire corona is above 1,000,000 degrees, but here it would be hotter, it's much brighter. And this is because of the underlying magnetic configuration. Over the North Pole and the South Pole, you probably can see on this image that there is a coronal hole, something that is darker. Coronal holes are where the magnetic field lines spread all over the heliosphere, sometimes even interacting with the galactic magnetic field. In the ecliptic plane, when you have these brighter regions, what we know is that actually the magnetic field will come out of the sun and will return relatively close to the surface. This is what we call closed magnetic field configurations. And these closed magnetic field configurations make harder for the particles to leave, and this is why the speeds are lower. So this is the message that Ulysses told us. When you get the brighter corona, the closed field line, you're going to get the slow solar wind. And in these coronal holes where the magnetic field lines are open, you're going to get the fast solar wind. But really with Ulysses, trying to understand this particular blob of plasma, this particular emission of particles over here, how it relates to the magnetic configuration of the sun, how it did open and how it released the particles, it was almost impossible because it is at several astronomical units. So really the cause and effect with Ulysses was really, really hard. Precisely what we're doing in this decade is trying to understand this in a much more quantitative way. This is what I'm going to be explaining the rest of my talk. But before I do that, I really want to put all these science in the context of the broader astronomy. I always have said that solar physics is the Rosetta Stone of astronomy, and that has been true for centuries. So it started with the measurements of chemical abundances and the spectroscopy, what were the composition on the sun. From the spectroscopy, we also saw the imprint of the convective motions in the spectral lines, and then we were able to see there is convection on stars. Then we went into stellar activity and the measurements with the Zeeman effect of magnetic fields on the sun, which then translated into stellar activity. More recently, we've got heliosismology, and heliosismology, as you all know, translated into astroseismology. Astroseismology is helping characterizing the planets that are that are orbiting the stars. We're characterizing, thanks to astroseismology, the stars and the planets as Jørgen Christiansen Dalsgaard, the Kavli Prize this year, explained yesterday. Well, I think where solar and heliospheric physics are going to be, again, the Rosetta Stone is precisely in what I say here, in how stars and planets are magnetically connected, how the stars create the astrospheres. And one thing that I want to mention is that, yes, it's important for the astronomical context because it tells us about the astrospheres. But then when this magnetic connectivity, and I'm going to be using this word a lot, magnetic connectivity, when the magnetic connectivity hits the Earth, we actually call it the space weather. So there is a very applicable component of this type of studies because it really relates on all these space weather effects that are so important for our technological society. What is the state of the art of the heliospheric modeling? You probably have seen this type of modeling. I still love to see them. I think it's impressive. Here what you have is a view from the North Pole of the ecliptic plane of the heliosphere. And at the center you have the sun, you have planets like Venus, the Earth, Mercury, Mars is over here. And there are a number of satellites. These are the squares that you see here, mostly at one astronomical unit. So what is what you see here? You do see like a spiral. This is the Parker's spiral. This is the most basic component of the magnetic connectivity. How do we get to do it? Because as you see here, it's moving. Is this just a numerical simulation? It is a numerical simulation. There are equations that we are solving here, but it's driven by data. The data, of course, being magnetic connectivity, is magnetograms. We start with magnetograms, and here you have a magnetogram taken by the GONG network. It's a network operated by the National Solar Observatory. We take the magnetic fields. We do a coronal extrapolation. On top of the coronal extrapolation, we put a solar wind solution, and we get Parker's spiral. And this is this spiral that you see connecting the entire heliosphere. On top of that, you see these clouds that are propagating. These are the coronal mass ejections. And there was a symposium here about coronal mass ejections on other stars. This is a very hot topic. We, of course, see them on the sun, and here we can even put it in the model. And you see up to 5 of them. The one that is very big, that is dark, this one is actually something that we think was similar to the Carrington event. It did occur, the last solar cycle, but we missed it, which was good news. The Earth was on this side. This Carrington event went this way, but stereo A, which is over here, was able to measure it, and it measured, I was talking before, the fast solar wind, 700 kilometers per second. This was more than 2,200 kilometers per second that the stereo A detected, but this time it missed the Earth. There are 2 points that I want to make about this modeling, because it's modeling that is entire heliospheric modeling that we do, is entire volume. How can we do the entire volume when we only see 2 pi? We only see the Earth facing side of the magnetic field. Well, that's because the models are not that good. One thing we need to do is wait for the sun to do a full solar rotation. And after the solar rotation, we say, okay, that's how the sun wants at one instant of time, which is not true. But now we know what the sun looked like for one full solar rotation. And then we put the extrapolation and the solar wind solution. But actually, the sun was never like this at any instant of time because we're not observing the entire sun. But we have to make that assumption, meaning that this connectivity modeling, they are not perfect. And of course, these connectivity models are used for space weather predictions, and they have this problem, that we only see half of the sun. At the end of my talk, I'll go of what we can do to improve that situation, that we are only observing half of the sun. So this is one of the comments that I wanted to make here. There are limitations with this type of modeling. It's data-driven. There is good physics there. You can put different levels of physics, but they do have this intrinsic limitation from the input data that we use for driving these models. The other comment I want to make is that you see a stereo A over here, at some point gets impacted by 3 coronal mass ejection. And here you have the snapshot when that occurs. So this is a stereo A in here. There are 3 coronal mass ejections impacting stereo A. And also there is this solar wind magnetic field line, this Parker's spiral that is very straight going on in here. So how can a stereo A detect, well, that particle comes from that CME or from the solar wind or from that other CME? Well, it's almost impossible. At 1 astronomical unit, everything gets mixed up, and it's really hard to distinguish what comes from where. What is the solution? What is the answer to being able to disentangle that specific process on the sun, created those particles? The solution is getting closer to the sun. The closer you are, the easier to make a cause and effect relation between what you measured in situ and what originated those particles on the sun. So this is the main reason why NASA and ESA decided that they need to get closer. It was one of the main reasons, one of the main drivers for both Parker Solar Probe and Solar Orbiter. Parker Solar Probe is a NASA mission. There are COIs from Europe. Solar Orbiter is an ESA-led mission, but NASA is heavily involved. There are PIs, and it was actually launched by NASA. Here you have the launch. The launch here was in 2018, here in 2020. So the 2 missions here, what they are doing is getting closer. And now you know why it's important for us to get closer for understanding better this magnetic connectivity. It's all about understanding the magnetic processes that release the particles that we measure in situ. These magnetic processes have the properties that are small scales, they occur very fast, and you need a microscope to really see what those processes are. And you need good spectroscopy, you need to have as much information as possible to understand how it all originates. Thankfully, the National Science Foundation, almost at the same time, has started operations of the Daniel K. Inouye Solar Telescope. This is operated by NSO, and it's a microscope, and it's helping us to understand what these physical processes are that then will be measured in situ by Parker Solar Probe and Solar Orbiter. So this is the combination of these 3 facilities that really is enabling this multi-messenger era. I have here a list of other existing satellites, other existing ground-based telescopes. All of them are important, all of them play a role, but these 3 facilities have unique properties, Parker Solar Probe and Solar Orbiter being closer. The Daniel K. Inouye Solar Telescope being more sensitive and better resolution than ever, that really are going to make quantitative this multi-messenger era that we've been discussing this week. What I'm going to be doing in the rest of my talk is actually describe DKIS, then with some details, of course, because it is operated by the NSO and is relatively new that we have started operations. I'll be saying something about Solar Orbiter, moving to Parker Solar Probe, And then I'll put 2 science use cases that really show how we're going to combine the data from these missions. So this is what is left in my talk. Let me start with the Daniel K. Inouye Solar Telescope. It's operational on the island of Haleakala. You have it here in Hawaii. And here it is, observing the sun. I like to always show this graphic over here because it tells you one thing. You see the direct light from the sun, and the beam of light that is hitting the primary mirror is not obstructed by the secondary mirror or by the spider of the secondary mirror. It's an off-axis configuration. Why is it off-axis? Being off-axis makes it bigger. It's a more complex system, but it is important for observing the solar corona. And as I was showing with the Ulysses image, we want to see the fluctuations in the solar corona, how they drive the particles and what you measure in situ. With Dickies, from the design phase, we wanted to observe the solar corona, and we benefit from a number of things, like the skies in Hawaii. They are clean skies, and they are very good for observing the solar corona. But then we had to do Dickies off-axis, and as you'll see, we have other properties of the telescope that help us observe the solar corona, which is actually very dark compared to the disk, of course. The main properties of Dickies, the main high-level requirements, are all described in here. I'm going to explain the 4 meters in a second because I know that always needs an explanation for our astronomer colleagues. But other components of Dickies that are important, that were crucial, and that were in the design phase from the beginning, is that we are able to observe multiple lines at the same time. This is important because this is the way in which we understand how energy is transferred through multiple heights. It's all about understanding these magnetic configurations, how they evolve, how they release particles on the solar wind. So for understanding these magnetic configurations, you need to do sensitive and accurate polarimetry. And this was included in the definition from the beginning of the telescope. It's not an afterthought. Every other solar telescope, for the most part, is an afterthought, and then you need the careful calibrations. Here, you need careful calibrations, but we are facilitating the effort for the community. And then, as I said, we are observing the solar corona. We can observe the solar corona half a solar radii from the solar limb. I'll give some more details, but what I want to explain next is why 4 meters. In solar physics, we're trying to answer a number of questions, and I have here 2 examples. The first one, where you have here an animation, is whether there is a second dynamo on the sun. I'm sure you all know about the main dynamo, the dynamo that produces sunspot, the dynamo of the solar cycle. For some time, simulations mostly are telling us that there is a second dynamo, a dynamo driven by turbulence. But it's still a dynamo that takes kinetic energy and transforms this into magnetic energy, and it can be actually coupled to the main dynamo. So it is important to know if granulation, if turbulence is driving a dynamo on the sun or not. And the simulations tell us what do we need to really see these dynamo processes driven by turbulence. As you can tell in here, and these are the intergranular lane, these are really small scales. Not only they are small scales, but the fields are disorganized, and they are really even smaller than what the granulation provides. And everything happens very fast. So you need to have good spatial resolution, temporal resolution, and sensitivities. The example that I have next to it is we're trying to understand how the energy transfers through different layers, as I said. One of the layers that transverses the energy is the chromosphere, and you have to use chromospheric lines. Chromospheric lines are never helpful. They are too deep, too few photons, the signals are too weak. So we know what the parameter space is needed to really do a good job in understanding all these physical problems. Solar physics needs to be in this parameter space. Solar physics needs to be able to achieve signal to noises of about 10 to the 4, these spatial resolutions and temporal resolutions. We are not there. We can do 10 to the 4, but then this is mostly 10 arcseconds, and then this takes minutes. We can do 0.1 arcseconds and 10 seconds exposure times, or even shorter, but then you barely get to 10 to the 3. So we're not here. To be there, what you can do is take the same equation that you use for when you go to a telescope and you have a star of a given magnitude, and you want to know for how long you need to expose. You'll be solving for the exposure time. Here, what I'm doing is using this data and solving for the diameter of the telescope, given the surface brightness of the sun, or the disk of the sun. And then you get 4 meters if you solve for that equation. This is why Dickies is 4 meters when you're observing the disk of the sun, and you're trying to achieve these parameters, you will need 4 meters. This is also why the European Solar Telescope is 4 meters. And that's not talking about the solar corona, which is much darker. For the solar corona, we're not trying to achieve this parameter space. If you put this parameter space for the solar corona, you'll get a much bigger telescope. And maybe one day we'll be asking for that telescope, not yet. We're going to benefit from what DICIS provides us, which is a lot compared to what we have so far. So here you have DICIS, already operational, observing the sun. DICIS is 4 meters. One of the things that you need to do is to manage the heat load. There are 13 kilowatts at prime focus, and this is where we are managing the heat. We are mostly removing most of the heat and sending it somewhere else. But really, it's a thermal problem, as almost anything that we are doing these days in solar physics, it is a thermal challenge. What you do see in here is the CUDER room. This is where the instruments are. It's a type of clean room. This is important for having robust data that goes smoothly through our pipelines. DICIS construction ended in November last year, impacted by COVID by about a year and a half, but we have started operations. We are in what we call operations commissioning phase. We probably are going to be in this commissioning phase until sometime in 2023. What we mean by commissioning is that during construction, we tested most of the components of the telescope, but really not all the multiple combinations of the instruments that we can do, which is almost infinite. So what we're doing during commissioning phase is testing all of these configurations, and we call this shared risk. We're telling the community, submit proposals. Proposals are evaluated by a time allocation committee, but we're saying, well, it's going to be probably the first time we're trying this configuration, so you should know the data might have problems. You should be helping us and collaborating with us for improving our pipelines. And that's what we're doing with the community. The first call was released in 2020. We got 101 proposals, which is a fantastic number for a solar telescope call. 50 of them were accepted by the time allocation committee, and we're slowly executing them. The second call is now out, and for the first time, we're also offering observations of the solar corona. To observe the solar corona, I said already 2 important components that help us: the skies in Hawaii, then the off-axis configuration, but we need to do a bigger effort because, again, the corona is really very dim compared to the solar disk, of course. We have in the configuration of the telescope a pupil Lyot stop that minimizes straight light. But we go one step further, and this is something we're offering in this second call. If you really want to observe the solar corona, we allow for including an occulter that avoids all the direct light into the telescope, and then you are able to see the solar corona. This is how much of an effort we need to do to be able to do the spectroscopy and the polarimetry that we want to do for understanding these processes that give rise to the heliosphere. So it's a big effort, but it's a unique capability that really has a very steep learning curve. But I think it's going to produce fantastic science because it's the first time that with sensitive spectroscopy and polarimetry, we're going to be observing the solar corona. Observing the solar corona, you can put these occulters, you can be off-axis, but of course what you'll see for the most part is the white light corona. Now, thankfully, there are these type of spectral lines that allow you to do the spectroscopy. And look at the species. So this is iron-13. So this is the million-degree solar corona. These are heavily ionized species. There is silicon-10, sulfur-11, silicon-9. All these species, the permitted lines are in the ultraviolet, but the forbidden lines are in the infrared, and these are the ones we're using to observe the solar corona. And also, thankfully, all these lines have some magnetic sensitivity of different types, and the sensitivity depends on whether it's more the Zeeman effect, the Hall effect. They are also sensitive to scattering polarization, and all of them through complex combinations and complex analysis. There is a lot of good quantum physics involved in understanding the signals from these lines. We're able to observe the magnetic field of the solar corona in details that are totally unprecedented. And as I said, highly ionized species, so we are able to observe the million-degree solar corona from the ground on a regular basis. So this is the introduction for DICIS concentrated on the solar corona. And now moving into the Solar Orbiter mission. Solar Orbiter was created from the beginning as a multi-messenger mission. because it included a complex in situ payload, mostly over here, but it also included a very complex and powerful remote sensing suite of instruments that you can see in here. Actually, Solar Orbiter is also a thermal problem. It has a heat shield, but then the telescopes, to be able to observe the sun, the heat shield has openings and a window, a door that when it opens, they are able to observe the sun. These are all the remote sensing instruments. I want to say that I think here in the audience, there are 3 PIs of different remote sensing instruments of Solar Orbiter. But it was a multi-messenger mission defined in this way from the beginning with this suite of in situ instruments and remote sensing instruments. Not only are good and complex instruments, but there are pairs of instruments that are thought to help this magnetic connectivity. In particular, there are 2 pairs. One is this one that I have in here. This is magnetic connectivity via composition, via chemical composition. You measure the chemical composition in situ with the solar wind analyzer. Solar wind analyzer measures protons, electrons, alpha particles, but also heavy ions. And you know the chemical composition that you measure in situ. Then Solar Orbiter has this spectrometer, the SPICE spectrometer, that can tell you the composition on the sun. If you see similar composition, you probably can tell I'm connected there. We're trying to understand where are we connected, how the process on the sun have an impact on the heliosphere. So this is one way of doing magnetic connectivity via chemical composition. But of course, Solar Orbiter also has another way of doing connectivity, which is via magnetic fields. Solar Orbiter has the polarimetric and helioseismic imager, PHI, which is a magnetograph, similar to the data that I was showing from GONG. It provides magnetograms. And with the magnetogram, you can do the same exercise of putting a coronal extrapolation, then a solar wind solution, and saying wherever Solar Orbiter is, the local magnetic field should be oriented in this way. And then it has a magnetometer that compares with that prediction and says, well, yeah, it's correct, or no, I'm wrong. And it helps define what the connectivity is. So there are this suite of combinations that help us either through chemical composition or magnetic field have a better understanding of where are we connected on the solar surface and compare with what we measure in situ. So that was defined for Solar Orbiter from the beginning, and that sense is a multi-messenger mission from the start. Another property of Solar Orbiter is that it doesn't go to Jupiter, it goes to Venus. Venus is not as powerful, but it does gravity assist and it kicks out the mission from the plane of the ecliptic. At the end of the mission, it's going to reach about 30 degrees. So we're going to be able to do something similar to what I showed with Ulysses, these images of the solar corona and what the particles are, but this time from the same suite of instruments on the same platform and taking on a given day. And we probably can repeat this in different conditions, and that would be something that we couldn't do with Ulysses that far, and Ulysses didn't have any remote sensing instrument. So that's a very unique property of Solar Orbiter, but it will be more towards the end of the missions, at the end of this decade, mostly. Let me now move on into Parker Solar Probe. Similar in the sense that it's getting closer to the sun, but very different. Parker Solar Probe has a heat shield. It's another huge thermal problem, but there are no openings on the heat shield because it's getting so close that there are no telescopes looking directly to the sun on board Solar Orbiter. There is a telescope, there is an imager, but it's looking to the heliosphere, never directly to the sun. Parker Solar Probe measures in situ particles and fields. An important property is that it really gets very, very close. I'm sure many of you have seen in the media that Parker Solar Probe has touched the sun. What is what we were saying when we were saying, well, Parker Solar Probe finally touched the sun? What we were saying is that Parker has entered into the birthplace of the solar wind, into the subalvenic corona. This is the region of the corona where the particles are being accelerated, probably from some heating processes that hit the corona and accelerate the particles. And then they go into the superalvenic solar wind. This is the solar wind that we measure most of the time. Once it is superalvenic, it's not dynamically connected back to the sun, it just flows in the heliosphere. But while it is still on the subalvenic corona, it is dynamically connected to all the processes that are occurring in this part of the corona. This is what Parker is targeting. And it's going to spend there like 100 hours. Parker has already entered this subalvenic corona, and this is from encounter 8. Parker has done 12 so far, and there are still 10 more to go. How do we know that they entered the subalvenic corona? Well, it's mostly because of this alvenic Mach number over here. When you see it's below 1, we know we are in this subalvenic region, where the heating is occurring, where the acceleration is occurring. So this data is brand new. It's never been observed so far. It's data that the community is using, and from what we heard during the symposium, there is a number of papers coming out from what they are finding in this subalvenic region. It's going to be really brand new science. This is where the coronal heating is actually occurring, and now we measured in situ how these processes have occurred. This is the touching the sun that was in the news, and you probably have heard about it. You probably have heard about that too. This was something that Parker found on the first encounter. It's called the switchbacks. And this is my first science use case where I'm going to combine Solar Orbiter, Parker Solar Probe, and Dickies. These switchbacks are observed by Parker as soon as you go below 0.3 astronomical units. So this is in the superalvenic corona. You don't need to go into the subalvenic corona to observe them. And what these switchbacks are, and they're very important. The community is really focusing on how they are created and the implications. Well, the importance is the following. Remember the image that I showed from Ulysses, where there is like a bipolar configuration. There is one polarity over the North Pole and another polarity over the South Pole. And then these magnetic field lines that are open create the Parker's spiral. So what Parker was supposed to measure was the Parker's spiral, and actually it did that. So you see this is the negative part of the Parker's spiral, negative polarity. Then it jumped into positive polarity, but it's still more or less the Parker's spiral. And then when negative polarity, this is also the Parker's spiral, and it did a number of jumps over there. But superimposed on the two polarities spiral, you have this forest of up and down jumps, where you are here, you are measuring a negative polarity magnetic field, but all of a sudden you encounter a positive oriented magnetic polarity and then back to negative. So the idea is, what you see here in the cartoon, you don't have a straight magnetic field lines, you have magnetic field lines that are kinked in this way, and this is what we call a switchback. Why are they important? Mostly for two reasons. One is that someone is doing work against the magnetic field and is bending the magnetic field. If someone is doing work, maybe there is some energy deposition, and maybe there is some impact on coronal heating. We're trying to understand how the solar corona is heated, and maybe this is a fingerprint of coronal heating processes. We don't know yet, but that's one reason why they are potentially important. The other is angular momentum losses from the sun. Really how they occur and when they occur can impact how fast the sun can lose the angular momentum, something that is very relevant for stellar physics, and we discussed this to some level during our symposium. So these switchbacks are important. Probably all astrospheres sufficiently close to the star have a similar configuration. Where Parker measures this is when it's connected magnetically to a coronal hole. Parker, most of the time, and Solar Orbiter are connected to coronal holes. Coronal holes is where the open field lines span over the heliosphere. So it's very easy that most of the time they are connected to these coronal holes, and every time they are connected, Parker Solar Probe measures the switchbacks. Solar Orbiter is getting into this 0.3 astronomical unit. It hasn't measured as many of them as Parker yet, but it will soon, and we are really looking forward to see how these switchbacks reflect on Solar Orbiter instruments. Now, what are the theories that are available for how are they created, the switchbacks? Of course, as soon as they were detected, soon after the launch in the first encounter of Parker Solar Probe, the community started with a number of ideas, and there are mainly two types of ideas about the creation of the switchbacks. So the first one is that they originate deep in the atmosphere and then they propagate outwards. The idea would be what you have in this cartoon. The red line here is an open field line, is the one that creates the heliosphere. Fast solar wind is streaming out from there. But then we know that everywhere on the sun we have these loops, these tiny loops that are bipolar and that are actually almost everywhere. It's really easy to see them in many places. So these open field lines are actually subject to what is called the global circulation of the open field lines. This global circulation is linked to the solar dynamo. And while they are moving through the solar surface, they will encounter these closed loops in here. If the orientation is correct, what it can happen is that there will be magnetic reconnection between the closed loop and the open field line, and you create the kink, and then the kink propagates upwards. This is one of the possibilities. This is called interchain reconnection. Interchain reconnection was proposed by Lenfix decades ago. And the question is whether this is the resulting consequence in situ of the interchain reconnection proposed by Lenfix. I also want to call your attention into the fact that as soon as you connect a closed loop with an open field line, there is a new connectivity that is created. The chemical abundances of this closed loop is closer to photospheric abundances. The chemical abundances of open field lines is different. We don't understand why is it different, but it is different. But as soon as an open field line with the coronal abundances connects with a photospheric abundance, you can have different abundances through these open field lines because of the new connectivity. And I'll get back to this in a second. The other way of producing these switchbacks is simply from the natural evolution of the expanding solar wind. There's a theory that the expanding solar wind is through transverse Alfvén waves that will be producing heating in the corona. And then the idea would be, well, these Alfvén waves have a nonlinear evolution and creates the switchbacks. These are the two groups of ideas. And what is important is that deciding between one or the other, I think, is going to be solved via a multi-messenger approach, as I want to show in the next slides. So for the first idea of this interchain reconnection, what is important is the existence of these bipoles. I want you to look at this imaging here, because the existence of these bipoles is, as I said, something that we know on the solar surface, but then you need sensitivity and you need resolution. So for example, here, you have the dominant polarity, which is black. It's a magnetic field line into the sun. And this is observed by SDO-HMI. SDO-HMI is a great instrument for many things, but it has a limited resolution and sensitivity. If you observe the same region at the same time as we were able to do with the Sunrise IMAX, this is the instrument that I led, you will see that this black feature over here actually is dominated on the other part by white opposite polarity features that are interacting with it. This is what can lead to interchain reconnection. This was an active region. It was not the type of regions on the sun where Parker was connected, but it's an example that by having good resolution, good sensitivity, you see more bipoles than what you see otherwise with other instruments. So this is a target for DKIS. We really want to go to the coronal holes and tell DKIS how many of these bipoles are per unit area, per unit time, and how does it compare with the number of switchbacks that we measure. That's the first qualitative comparison that we can make. There are observing proposals being prepared for DKIS to try to understand what is these magnetization levels of the coronal holes and compare with the number of switchbacks. So this is an example of combining Parker Solar Probe and DKIS data. One thing that I want to mention is that from Parker Solar Probe, we know that these switchbacks know something about convection on the sun, because they do occur in patches, and these patches have been translated into supergranular areas. So the switchbacks occur depending on how convection is organized on the sun, and there are these supergranular patches, and that tells you that the switchbacks may be coming from deep in the interior because they know about these supergranular lanes, where the magnetic field is concentrated. Not only that, in Stuart Bale, in this paper, he detected an increase in the abundance of helium on the switchback. As I said, when there is the reconnection, there might be a change in the chemical composition. And actually, what we know is that the switchbacks have an increased helium abundance. And I'll get back to helium abundances. But that's another indicator that it can be from these reconnection processes because it has a different abundance of helium. This one would be the explanation for the nonlinear evolution of the Alfvén waves. This is a theory by Steve Kramer. He made this figure some time ago. This is how he thinks Alfvén waves, which are transverse. This is why you have transverse motions in here, are created on the solar surface. He's comparing a number of transverse motions. This figure is interesting because this is the solar surface, and this is more than one astronomical unit. So the Earth is somewhere here. So he's comparing here in this figure the entire heliosphere. So you have on the sun transverse waves that are observed in the corona, in the chromosphere, at the solar surface. And then there is transverse magnetic motions measured by Ulysses. He's already put in data from Parker Solar Probe, and he needs to dump the energy and release the energy somehow. But what he's saying is that really what he's expecting to do is to combine the in situ data from Solar Orbiter and Parker Solar Probe and the observations from remote sensing from both Dickies and Solar Orbiter to be able to make that image for a single case. Here, when he did this image, these images are taken by decades apart. The corona was observed by one satellite. The chromosphere was observed by a different telescope decades apart. And these measurements were even even before the measurements of the solar corona. Of course, the Parker Solar Probe measurements are newer. He needs to do this for one single case where we see the transverse motions in the photosphere, then in the chromosphere, then in the corona, and then finally in situ. That can only be done via the combination, this multi-messenger combination. And this is why I'm saying whatever the solution is going to be a multi-messenger solution for whether it is more the nonlinear evolution of Albert waves or interchain recollection. So this is one science use case that we're going to do because it's related to coronal heating. It's crucial to the science of both missions and of the Daniel K. Inouye Solar Telescope. This is another science use case that goes into the helium abundances that I just mentioned. This one is more difficult. This one is about observing the solar corona. And I said that with Dickies, observing the solar corona has a steep learning curve. But I think it's still exciting, and it shows the interest of this multi-messenger approach. What I want you to focus on is on this part of the diagram. What I have here, this is the solar activity cycle. It's solar minimum, then it goes into maximum, then it goes into minimum. And what we're measuring here is the helium abundance. Just look at what happens at solar minimum. Same happens at solar maximum, but at a lower level. So you look at the solar conditions at solar minimum, what you'll see, these are different speeds of the solar wind, and they have different abundance of helium. So the fastest solar wind has the highest abundance of helium. Photospheric abundance is 8%. So the highest abundance that we see of helium in the solar wind is 5%. So there is a process that depletes helium. We don't know what the process is, but it's always lower than the photospheric abundances. But if the solar wind is fast, the abundance is 5%. If the solar wind gets at lower and lower and lower decreasing speeds, the abundance also goes down. So it's a process somewhere in the corona that it says, well, I'm going to deplete helium, but because I'm doing an effort, and this is one way of just talking, because I'm doing an effort in depleting helium, I'm not able to accelerate the solar wind as much as I could. And the least that you do deplete helium, the faster it is. If you spend too much time depleting helium, then you're going to have a very slow solar wind. It's actually interesting that if you take this relation in here and you say, well, what is the smallest velocity that you're going to see for a helium abundance of 0? It is actually 250 kilometers per second, which is very close to the smallest solar wind that we have ever seen. So there is a process that depletes helium. We don't understand it, but it's clearly related to the origins of the solar wind. And Parker is actually measuring abundance of heliums. Actually, what it measures is alpha particles and protons, but it's measuring these helium abundances. Can Dickies and Solar Orbiter help with the remote sensing, understanding how it all originates on the sun? And we hope so, but as I said, there is a steep learning curve in here. But it shows that the funny part of this multi-messenger research that we're trying to do over the next decade is all about the configurations where the different missions are going to be. In this figure, the sun is here. This is the Earth. Dickies is here, of course. And they are fixed. But both Parker Solar Probe and Solar Orbiter are going through this type of complicated orbits. One configuration that we look forward to be able to observe relatively soon is to have Parker Solar Probe in quadrature, measuring helium. The helium that comes from that part of the sun, and Parker, very close, is going to be measuring helium. Then the question is, can both Dickies and Solar Orbiter be able to observe the corona on this side and measure helium with remote sensing and correlate with what Parker Solar Probe is measuring in situ. This is one of the targets that we're trying to do. Can Solar Orbiter and DKIS say something about helium abundances? And the answer is yes, but we need to test this ability to measure the helium abundances. Here you have a map of helium abundances by doing line ratios between helium-2, this spectral line in here, and METIS, Lyman alpha. This is not from Solar Orbiter, but these are prototypes from instruments that are prototypes similar to the ones in Solar Orbiter. And we have already produced helium abundances in the solar corona. You see the magnetic field lines here. These are not measured magnetic field lines. These are from extrapolations. But the helium abundances and the creation of the solar wind is always related to the topological configuration of the magnetic field. This is why they put it in here, but they are not measured. DKIS can measure them. DKIS can actually measure these magnetic field lines and understand what the real configuration is. And DKIS can also measure helium. This is one of the areas where we will have to train DKIS, and we will have to train the expertise to make sure that we're able to have these helium observations. Because what we know is that in the solar corona, we have observed these diffuse brightness components of helium. This is the million-degree solar corona. How can you have neutral helium in the million-degree solar corona? Of course, most of the time you're going to have alpha particles. But one of the things that we know is that the heliosphere is mostly a dusty plasma. There is a lot of dust in the heliosphere. And actually, Parker Solar Probe is interacting a lot every time it gets closer to the sun with this dust. So dust is a source of electrons, and the alpha particles interacting with the dust can produce a population of neutral helium. This is one of the ideas to explain why there is this diffuse helium in the solar corona that DKIS can observe using this 10A30 line. This is not a forbidden line, but this is one of the lines that DKIS can observe. And the idea would be, well, with METIS and with EUI in Solar Orbiter, we can observe helium abundances, not an easy measure, and we discussed this during the symposium. With the helium observations of DKIS, and where we can also measure the Paschen line, H1 at 1.3 microns, we can get a ratio, and we can also provide abundances of helium. Can we correlate these remote sensing observations of abundances of helium with what Parker is measuring? So this is one of the things that we're going to try. I think we need to expect until we understand how we can coordinate with both DKIS and Parker Solar Probe. Are we coordinating? And the answer is yes, we started this year. But as I said, DKIS started observations this year. So we are having here another learning curve about how to coordinate with these two missions. The first attempt was in February, but that was almost a coincidence. It was nothing serious. It was just that by coincidence, DKIS was pointing here, and we think Parker was connected nearby. But we didn't coordinate at that time. It was almost a coincidence. But then after that, we are discussing with the teams of both Parker Solar Probe and Solar Orbiter to really make coordination with both of them. That has occurred, and I'll show in a second. One of the things that I want to say is that this coordination is done via DKIS director discretionary time, meaning that the data doesn't have proprietary period. The PI-driven data from DKIS has a 6 months proprietary period, but this one is no proprietary period. So when we do this, we release the data as soon as it is calibrated, and that's what we're doing from the coordination campaign that occurred in June this year. This is June. This is 2 months old, so it's really something that we are doing and learning slowly how to do a better job. So there were these 4 days. It's only 4 days of campaign, partly because these missions move really fast. It's not that you have that much time. They are so close to the sun that they have to move really fast, in particular Parker Solar Probe, that the configuration for the quadrature only lasted 2 days. Again, it's all about where Parker Solar Probe, Solar Orbiter, and the Earth is. The configuration that we had in June, Parker was in quadrature, as I was explaining, but Solar Orbiter was actually on the far side, and Earth was here. Both Solar Orbiter and Earth were able to observe the solar corona, similar to the configuration that I was talking about. And Parker Solar Probe was measuring the in situ consequences of that solar corona observed by Solar Orbiter and by DKIS. This time, for these 2 first days, what we decided to do is to actually observe the magnetic field. I've been saying all along that whether you are releasing particles or not is all of a evolution of the magnetic configuration. So the first thing we want to do is understand with Dickies the magnetic configuration underlying the measurements of Parker's solar probe. And that's what we did for these 2 days. We already put some context images in helium, but we concentrated mostly in the magnetic configuration. And then Solar Orbiter was observing the solar corona, as it is said in here. 2 days later, Parker's solar probe moves projected on the disk as seen from the Earth. Parker's solar probe orbited in this way and then was on the disk. And what we did with Dickies was understanding where the pointing to Parker's solar probe consensus was and point Dickies there. The consensus pointing was somewhere in this facular area over here, and you see that Dickies did a mosaic. I'm going to show you data from Dickies obtained while we were pointing to this region in here. One thing that I want to say is that this data is fresh off the press. I mean, I saw it during the symposium. I didn't know we were already going to be able to show it. Thomas Rimmele gave a talk on Dickies, and this is data that has been just calibrated. What you see here? What you see is H beta. This is H beta, so it's a little lower than H alpha. The brightenings over here are the foot points of the magnetic field, but you see that there are canopies at both sides. The canopies probably are low-lying magnetic field lines that connect back relatively soon, close field lines. But in these regions, there are always some number of open magnetic field lines. We need to understand how many there were. I'm doing analysis and extrapolations over here, because it seems Parker was connected somewhere here. And we were able to obtain this data with Dickies, as I said. This is data that I was able to see for the first time. I think it's pretty spectacular this week, and it will be available for the community as soon as we finish the entire pipeline for calibration. So what we have in here is this Parker Solar Probe consensus magnetic connectivity. What do we mean by that? So the question is, when Parker is connected somewhere, we want to point Dickies there. But do we know for sure where Parker is connected? As I said, as it is said here, it's a consensus pointing, meaning that there is people doing these connectivity studies, these Parker spirals that I've been talking about, that I said they are not perfect. They cannot be perfect. We have to assume the sun is the same for a solar rotation. People put different physics, they get different places for connectivities. During the symposium, we've been discussing how different people are doing this type of things. And then if there is a real consensus, they tell us, well, we think Parker is connected there, and you point Dickies there. So here you have one of the Sam Batman doing this type of connectivity studies in 2 different coordinates. So if you just get, Parker Solar Probe is the blue dot that is moving there. At any given time, get the magnetic field line that Parker is going through, and then project it back on the solar surface. You're going to end up, nobody knows where, somewhere here. Parker is, of course, on the solar ecliptic plane, but the connectivity can be anywhere in the solar surface. And the way we know where is it connected is via this type of modeling that, as I said, different people do in different ways. And then we get some consensus of where to point. But we need to improve. We need to make sure we're pointing an instrument like Dickies to the right place where Parker is connected. And as I said at the beginning of my talk, we only observed 2 pi, and that's a problem. This is why I'm calling here 4 pi. 4 pi is what solar physics and solar and heliospheric physics is going to do over the next decade. I'm sure that for the heliospheric decadal survey, there are going to be a lot of discussions about how to fill the entire heliosphere with magnetograms to observe the solar magnetic field all the time, all the sun. But we cannot do this now. It's something that is being proposed by the community and will be discussed as part of the decadal. Can we do anything any better? And the answer is yes. Yes, thanks to 2 things that I'll be mentioning. The first one is that, yes, we see 2 pi. But thanks to heliosseismology, we actually see the far side of the sun. How is it that we see the far side of the sun? I'm not going to enter into the details, and I hope Jürgen lets me explain it in this way. Heliosseismology is all about observing the interior. Well, if you keep observing the interior, you actually get out on the other side, and you'll sense what the other side of the sun is. This is all about how the acoustic power travels on the solar surface, but we can sense magnetic fields that are on the far side with observations from the front side. This is a well-understood technique. NSO has been providing these far-side maps since 2006, and every 12 hours, you really cannot go much faster, you can provide a map of how the far side looks like. This is one of our maps, and here, this dot is that we're saying there is a sunspot on the far side of the sun. And we're able to sense that, which is something that is one of the many amazing aspects of Helios seismology. And this is important. It's important for the modeling that we're trying to do here and that I've been explaining. Let me show you an example of how important it is, even though this is more in the context of space weather. So this is work done by Nick Argy, where he said, well, the data from stereo, in this case, is the black line in here, and he has a model of connectivity, one of these models of Parker's spiral. Well, when he was not using far-side data, he was really missing this part in here. The model was predicting the blue dots, and he was missing these high-speed flows. He was not able to predict it with his model, but as soon as he put the sunspot on the far side and the active region, probably that active region moved a coronal hole to somewhere else, and then he was able to predict correctly the magnitude of the speed of the solar wind over here when he was not. So it really makes a difference to include this far-side data, and we're starting to incorporate this into the modeling. We had a number of presentations during the symposium. One of the problems is that the far side is Helios seismology phase shifts. They don't have any information about polarity. But through artificial intelligence, it seems people are able to start putting some level of magnetic field polarity. Of course, if it is artificial intelligence, you need to be able to feed this with good data. And the good news is that we're starting to have good data. And here, what you see on this image on the right is a far side map from NSO. The far side here is the dark orange over here. This part is observable from the Earth. You see, these are the phase shifts that are created by Helios seismology on the far side that tells us that there is some magnetic fields in here. But with Solar Orbiter, with the instrument Phi, we can already start observing the far side. And this is one of the images from the Solar Orbiter Phi magnetogram, where we were able to see the magnetic fields that we don't see from the Earth. And sure enough, for this signal in here, you do have magnetic fields. And actually, in this case, the strongest signal is the one that you see here. And there is another strong active region here. So we can now start using artificial intelligence and combine these phase shifts with these observations from Solar Orbiter to feed the process of artificial intelligence and always provide polarities and then improve these magnetic connectivities. This is work that was presented by Hannah. She's here with us in the audience during the meeting. She has a lot more far-side maps, and this is a very promising technique for improving this magnetic connectivity. At NSO, what we're doing is what I said at the beginning of my talk. I said, we only see 2 pi. We're trying to produce maps, but we have these gaps. This is the 2 pi gap. This is the 2 pi that we see. This is the 2 pi that we don't see. We can fill this 2 pi that we don't see with far-side maps, and perhaps with artificial intelligence include some level of polarity information. But with Phi, with Solar Orbiter, we can even put real magnetic field information. So this is what we're going to do. We're going to try to incorporate all this new data into our modeling of the Parker's spiral of the magnetic connectivity. And this is really going to help us to say, okay, get dickeys and point it exactly there, and we're going to be more accurate and more precise because we'll know better what is this magnetic connectivity of the sun. This is what we're doing as part of the NSF's multi-messenger program. NSF bought the idea that this is good multi-messenger science, and they've been funding NSO for a number of years. We're doing this funded by the NSF. We're going to be able to tell dickeys where it should be pointed, and I think this is going to be really exciting time, so stay tuned. Thank you.
Thank you very much, Valentin, for this excellent talk. And so I think that now we will take questions from the audience, if there are any. And I also encourage the people that are watching online to write questions in the chat. I already have one. So please.
Hi, Valentin. This is Dave Soderblom. You said something a few minutes ago that really took me by surprise, and that was the existence of dust close into the sun. Is this the first time this has been known? And what do we know about this dust? Where does it form? How does it form? Particle sizes? What do you know?
Yeah, this is a very interesting question. And actually, I think what is relevant, no, I think it's been known for some time. It was expected. So we were expecting that Parker's solar probe, as it gets closer, it was going to encounter dust. But it's encountering more dust than what we think it would. We thought it would encounter much less, but it's encountering a lot of dust. How Parker measures dust is interesting because it doesn't have a dust monitor, but the antennas measuring magnetic fields and electric fields get spikes every time they hit the dust particles. So they are able to actually find where the particles are coming, what type of micrometeorites are originating this dust. And it is something that was unexpected, how much dust we are encountering. So we knew that there is a dust. We also know that if you get sufficiently close, the sun will sublimate the dust. It will.
Yeah, exactly. How close then is the dust being measured?
Well, this is one of the scientific targets of Parker Solar Probe, understanding when the sun gets sublimated and you get a clean heliosphere. So far, it's been very dusty, and they haven't found it yet. Really, where they are going to be able to tell us when the dust is sublimated and they have a clean part of the inner heliosphere close to the sun, is going to be more from the heliospheric imager. The heliospheric imager, which is like a coronagraph, is the one where we are expecting that as it gets closer, we'll at some point start seeing a reduction in the amount of dust. I believe they have already seen a reduction, but again, it's less than what they were expecting. Even at the mission level of Parker Solar Probe, they are a little concerned with the amount of dust they are encountering. So it's an interesting problem, and it's a serious issue for the mission.
Interesting, thanks.
Yes, please. I have an echo.
Yeah, there's an echo here.
Please.
Hi, Tom Statler from NASA headquarters. Thanks for a great talk and for teaching me a lot of things that I did not know about. The variation in the helium abundance as a function of solar cycle and speed, that is absolutely fascinating. What about species heavier than helium? Do we have information, and is there something interesting to be found there?
Oh, I'm sure there is, I'm sure. Because actually, the elements are different depending on the first ionization potential. And helium is particular because it's the highest first ionization potential, but there are others that are there, and it's probably depending on this first ionization potential. Now, the problem is that we don't have that many measurements. The one that I was showing here about the changes with the solar cycle, this is from L1. So this is done at L1 near the Earth by the ACE satellite. So I don't think I've seen any heavy ion sensors on ACE. So it's all about helium, alpha particles. But Solar Orbiter has a heavy ion sensor on board. So Solar Orbiter is going to be able to tell us whether this is also true for heavier species. Absolutely.
Thanks.
It's fascinating. These helium abundances, they really tell us something that we don't know about the solar wind.
Hi, this is Eunkyung Lim from KASI. Thank you for the very educational lecture. My question is, the switchback sounds like a hot topic driven by the Parker Solar Probe. If the interchange reconnection at the lower atmosphere is the real mechanism of this switchback, then shouldn't we be able to observe the similar configuration in the lower atmospheric observation, like the inversion of the polarity science or something like that?
Yeah, it's not going to be easy. Well, let me say, yes, switchbacks are really, really hot topic. I know of people that go to solar workshops and they are counting the time until someone mentions switchbacks because it's what everybody's talking about. So switchbacks were known. Ulysses measured them, but not by that many as Parker Solar Probe. The number of switchbacks that Parker Solar Probe has found is totally staggering, much many than what ever Ulysses did. Then about your question of are we going to be able to actually map deep in the interior with some form of inversions, switchbacks? Well, hopefully yes, but it's going to be really hard. It's going to be really hard. I think at most what we can do is a statistical comparison of how many switchbacks you measure versus how many cancellations there are at the solar surface. Really being able to track and map a cancellation event where you see, okay, actually a switchback was produced and we see an outflow of the switchback. So it's really the picture that I show on interchange reconnection is going to be hard. We should try. We should try. And as I said, it's all about this very steep learning curve in all of this multi-messenger science that we're trying to do. I think the first thing is to make the statistical connections to see, okay, there are as many cancellations per unit area, per unit time, as you need to explain the number of switchbacks detected by Parker. And then once you know that this is the case, try to map one in detail, for which, of course, I would use Dickies by all means. So, yeah. Let me say one thing. During the workshop, the METIS instrument in solar orbiter showed an image where the idea is that this was a switchbacks. Actually, the image that was white light continuum, and in white light continuum, you would see something that looks like a switchback. It is tentative. I'm not sure if I fully buy the idea, but we're looking for them, absolutely.
If I may interject, there is a question on the...
I thought you were going to see that the METIS was a real switchback.
No, there is a question related to switchbacks in the virtual platform, so I thought of just going now. So do you have a sense of what are the energetic inputs that are needed to generate the switchbacks at the rate that is observed? And how this compares to the total energy losses of the chromosphere and the corona?
Oh, no, I cannot answer. This is a great question. And all I can say is that we are bringing to some of the Dickies proposals the in situ community. One of the problems we're facing here is that the in situ community, they have a language that is different from the language that we use for remote sensing. And even though it's the same process, it's the sun and it's the heliosphere, understanding each other is one of the challenges that we're facing. This was a challenge for Solar Orbiter. So we're bringing Parker Solar Prof into our observations with Dickies, because only with them are we going to be able to do these estimates. With their close collaboration with the in situ community, it's critical that the in situ and the remote sensing communities work together here. So I don't have an answer, but I know this is a great question.
Okay, thank you. I thought there was, yes, please.
Hey, Valentin, that was a great talk and provided an opportunity to reflect on how much we know about the heliosphere, how much we don't, and still discovering. So one of the aspects that you didn't touch about and which I think is important for this broad community is how much we have learned about the sun and the sun-earth system, which provides a window to understanding star-planet interactions beyond the heliosphere. Would you like to comment a bit on that, on how the exploration of the sun and sun-earth interactions would help us define goals for understanding exoplanetary habitability beyond the solar system?
Yeah, I mean, this is a difficult question. One thing that I'll say is that these models, I stopped in Mars in one of the models that I showed. But people are bringing these models all the way to Jupiter. And it is funny because actually the Parker's spirals go several round trips before it hits Jupiter. So it really gets complicated as you move away from the center of the sun. I think what we're trying to do is understanding the origins, understanding the inner part of the heliosphere, and then we'll propagate this outward much more realistically, understanding what physical processes are important. And at some point, this will impact how we are encountering the galactic magnetic field and the heliopause and the physics there. Of course, NASA has missions that are going to target that region. And it's a process. It's going to take a century to understand it, but it's, I think, fascinating. And this is the role that I was saying. This is really the Rosetta Stone for transferring all this knowledge into how stars create astrospheres. I think that's all I can say. Because it's
Actually, again, there is a question in the chat which is somewhat related. So student astrospheres can only be done with remote sensing measurements. What are the challenges and approaches to learning about the particle environment around stars without in situ instrumentation?
Oh, wow. Anything that I said probably is not a good answer. So I probably will refrain to answer this. But to the person that was asking, what I can do is, I think there is no satisfactory answer. But I'll say, well, if they can drop me an email, and I guess I'm very easy to find, I'll pass the question to the in situ community. As I said, it's all about collaborating between remote sensing and in situ, which is always a problem. And see if they have an answer. I don't think we have an easy solution here.
Next week there is a symposium on stellar winds, and so
yes,
probably there will be a lot
so
of
absolutely.
information there.
Now, of course, for in situ measurements of astrospheres, we need to go there, right?
Well,
and I don't think there is any easy way to detect anything.
not anytime soon. Any more questions from the audience? Yes, please.
Marco Romoli, University of Florence. Thank you, Valentin, for this very nice synthesis of the state of the art of solar physics. I have a question about the future. Since, as you know, space missions, when you launch one, you need to think about what's coming next. This is an exciting decade. Will we solve all the questions of solar physics, or there's something that we need to do in the next decade in order to understand better?
Oh, yeah. So Marco is the PI of the MEDIS instrument. He showed that image that potentially can be a switchback. Marco, I think what we don't have yet is a good view of the solar poles. Solar orbit is going to do something, and it can do a beautiful job. But really, this 4π, and the 4π includes having constant views of the solar poles, is what I think we need to do. I think solar physics need capable missions that are going to L4, L5, L3, or orbiting at the plane of the ecliptic, but then also observing the solar poles. We need to observe the entire sun all the time. This is for space weather prediction, but this is also for understanding how it propagates beyond 1 astronomical unit, the entire magnetic field of the sun. So I think this is where solar physics is going to go. I know that for the Helio 2024 decadal that has started in the US, there is a lot of pressure for having these 4π views of the sun.
Thank you.
One more. We have a lot of questions.
Hi, Valentin. Thank you very much for this very interesting talk. You mentioned the joint observations between DKIST and orbiter and probe. It seems to me that there is some maybe duplication in the modeling efforts on the, for example, with the Parker Solar Probe community and with the orbiter community to know where to point and decide what to observe when. How do you see? Shouldn't we talk more or try to coordinate more?
Yeah.
How should we do that? You mentioned that it's difficult sometimes to talk between the in situ and the remote sensing, but maybe also between the ground-based and the space-based. So how should we solve that?
Well, that goes back to what I was saying, that the interaction between the in situ and the remote sensing communities are always hard. Right now is the science teams between Parker Solar Probe, Solar Orbiter, and DKIST talking to each other and collaborating and deciding what to do in the next encounter. Then there has to be a collaboration after the fact. Once the encounters have occurred, once the images have been obtained, we need to make sure that the community is using the data and again helping to bring the remote sensing and the in situ teams at the same time. I think this is crucial. As you know well, this was always crucial for Solar Orbiter. Now it should be broader. It should be the Solar Orbiter, Parker Solar Probe, DKIST, other facilities as well, that get together the community and try to make sense of what was observed on the sun versus what is measured in situ. Without the full expertise of all of these broad different communities, is going to be impossible. As you know, the in situ community, they are more of a plasma type of physicists. For the observation of the sun, we're astronomers. we need to understand each other and we need to collaborate, and there is a strong tendency to split and not to collaborate. That's what we need to make sure doesn't happen for really taking full advantage of this multi-messenger science.
One more, and then maybe we can all go for a coffee.
Okay. Thanks for a great talk. My question is a little bit related to this, particularly in this multi-messenger era. Usually with the observations, you want to include some kind of intelligence in how you schedule them. And particularly with Dickies, are you trying to think about that, some kind of intelligence in all these proposals coming in, and how you might actually schedule them to maximize the outputs?
Yeah, yes we are. But again, we have plenty of challenges here, and I can discuss offline with you. I mean, while you were talking, one thing that came to my mind is that I'm concerned, so I don't have a specific answer, but you reminded me that our nighttime colleagues also have an issue here. For them, multi-messenger is really combining two messengers, sometimes a third, which is gravitational waves from a neutron star merge versus remote sensing, understanding what is the electromagnetic counterpart with telescopes. So that's the same messenger that we're using. But they use gravitational waves, they use neutrinos. The physics there is very different from the one that we use in astronomy. So what we're talking when we say multi-messenger is about communities that use different physics, speak different languages, and where collaboration is hard. So we have the same challenge in solar and heliospheric physics as our nighttime colleagues. I don't have a good answer, but we certainly need to do what you are proposing, absolutely.
Okay, well, we have one more question on the virtual chat, and then we close it. So which of the new measurements from the KIST are you most looking forward to?
Okay, well, I don't know. DKIS is obtaining data as we speak, probably. And what is observed, and I'm going to let Ali mention something, is decided on that day. So I don't know what the latest observations of DKIS are, of those that have been obtained. The one that I want to make with DKIS, the one that I have an interest, I have said it here, I want to go to a coronal hole and understand what is the magnetization of coronal holes. That's the one that I think is now most important because of the connection with Parker Solar Probe. Of those that DKIS has already obtained, even the ones we've seen this week, they're great, and they are awesome, and I look forward to see it. I haven't had an opportunity to see it. Ali, you are connected. You want to say something about it?
Good question. What are we looking forward the most? I mean, we haven't started observing again. We will start next week, hopefully, entering the next observing window. We haven't even deployed all instruments yet. That is, I think, still something to consider as well. Right now, we just had started to offer another instrument, which we haven't gotten data with yet. So there's so much to look forward to. It is really hard to pin it down what would be the most interesting thing. I think it all will be interesting.
Yep.
Specifically in cycle 2, when we start looking at new spectral lines with the WISP, for instance.
So I said Ali because she's deeply involved with DKIS operation, but you should also answer.
Well, the coronal magnetic field.
Okay, the coronal magnetic field.
I mean,
yes.
this is
And I've
something
been
we
saying
all
that.
have been waiting for.
Yeah,
But anyway,
absolutely.
I think that we should close it here. It's been great. Thank you very much, Valentin. It was an excellent talk.
Thank you, everyone.
And thank you all for coming.